All right, I recorded. Hi, everybody. We have I think it's our third Statbytes seminar, a lunchtime seminar of the year, or of this. Yeah, it's of the year. No, we had one in December. It doesn't matter. But anyway, we have one of our Stat Lab tutors, Andrea Heredia, who's going to speak on Cox proportional hazards regression survival analysis. If you're looking for the videos, you can tell your friends, or your friends are looking for them. They are posted on the Stat Lab website. So, and I'm going to put the materials for this particular lecture, link to them in the chat. So you can follow along if you want, or access them at a later time. I think those will also be either the link or the materials will also be on the Stat Lab website. Okay, so Andrea, you can take it away.
Perfect. Okay. And please let me know if you all can see my screen and if it's on presenter mode. Yes.
You can
I
see
think it looks, yeah. Okay, awesome. I think at least it looks like it is. So first of all, thank you everyone for joining. My name is Andrea Heredia, and I'm a second-year Master of Public Health student specializing in epidemiology and biostatistics. And as Dr. Johnson was saying, I'm a Stat Lab tutor. And today my presentation is going to be on survival analysis, more specifically the Cox proportional hazards regression. I actually learned this in advanced data analysis last semester. So thank you, Dr. Johnson. So what are survival analyses and what are they used for? So basically, these are a collection of statistical techniques or methods that are used to address questions that have to do with whether and when an event of interest takes place, right? This event sometimes is death, but not always. Some examples of survival analyses are time the average person lives from birth, time after cancer treatment until death, time from HIV diagnosis until AIDS development. So survival analysis has different names in different disciplines. Sociologists call it event history analysis, economists call it duration analysis or transition, and even engineering researchers call it lifetime or failure time analysis. So why and when survival analysis is needed? So basically, the dependent variable in any survival analysis contains two pieces of information, which makes it different from dependent variables used in other more conventional statistical analysis, such as the independent t-test or even linear regression. This one actually takes time into consideration. So the first piece of the dependent variable is that it has to be a continuous variable, recording actual time. This can be days, months, weeks, as you can see in the graph, quarters, years. A study subject experienced a change process. And then the second piece is a change in state, like changing from state one, let's say the absence of a disease or of a defined event. And state number two is the presence of such an event. The common questions asked in statistical and survival analysis is what is the proportion of the population that's going to survive past a certain time? Or if they survive, at what rate are they going to die, etc. So while there are several types of survival analyses, these are the most common ones. So the Kaplan-Meier curve, the log rank test, and the Cox proportional hazards ratio. The Kaplan-Meier curve or plots are used to visualize survivor curves or time. It's a non-parametric method used to estimate the survival probability from observed survival times. The log rank test is to compare survival curves or survival times between two or more groups. This is also a non-parametric test, and it basically compares the observed number of events in each group to what would be expected if the null hypothesis were true. Since we're comparing groups, the null hypothesis is that all the curves or the survival times are identical. Something to keep in mind is that the Kaplan-Meier curve and the log rank test are examples of univariate analysis. So they describe the survival according to one factor under investigation, but ignore the impact of other covariates. Also, especially the Kaplan-Meier curve, actually both of them, Kaplan-Meier curve and the log rank test, are useful when the predictor variables are categorical. So comparing treatment 1 to treatment 2, male versus female. However, they don't work easily for quantitative predictors. So let's say age or weight continues, right? So the topic of this presentation is going to be the Cox proportional hazards regression, and it basically describes the effect of several variables on survival. Something else to keep in mind, and that I will explain in the next slide, is that for the Cox proportional hazards, well, actually all survival analysis, all survival data are generally described and modeled in terms of two related functions, the survivor function and the hazard function. Okay, so some important terms, concepts for survival analyses. The event, which is defined as death, disease occurrence, recovery, basically any experience of interest that you're studying. The time is the time from the beginning of the observation period, the beginning of your study, to the event, the end of the study, loss to follow-up, etc. As mentioned before, survival analysis focuses on the expected duration of time until the occurrence of an event of interest, right? However, sometimes the event may not be observed for some individuals. And that's what we call censoring or censored observation. Occurs when it's basically incomplete information. It happens when we have information about individual survival time, but we do not know about that case or subject after the time of censoring. A censored subject may or may not have an event after the end of the observation time. So censoring can happen in several ways. Most of the common ones are, for example, a patient has not experienced the event of interest, such as death within the study time period. A patient is lost to follow-up during the study period, or even a patient experiences a different event, completely different than what you're trying to study, that makes it really hard to follow up. So then we have survival function and hazard function. So the survival function is the probability that an individual survives from the time origin to a specified future time. And the hazard function, the probability that an individual who's under observation at a time t has an event at that time. Something to pay attention to is that in contrast to the survivor function, which focuses on not having an event, the hazard function focuses on the event actually happening, actually occurring. Okay. So the Cox proportional hazards regression, the purpose of this model is to evaluate simultaneously at the same time the effect of several factors on survival. In different words, it let us examine how specified factors influence the rate of a particular event happening. Again, it can be infection, it can be death, it can be anything at a particular point in time. And this is commonly known as the hazard ratio. And the predictor variables that we're talking about, or factors, are termed covariates. Okay, so because of the topic of the presentation, an equation has to be included, but all the components are described and explained in simple-ish terms. So the Cox model is expressed by the hazard function, denoted by HT. And this function can be interpreted as the risk of dying at time t, right here. So the t represents the survival time, the ht, again, the hazard function, determined by a set of covariates. Our coefficients, or our betas, measure the impact, the effect size of these covariates. H naught is the baseline hazard. And it corresponds to the value of the hazard if all of the covariates are equal to 0. And again, time in the HT reminds us that the hazard may vary over time. To put it, okay, so to explain a little bit more what the hazard ratio, or how do you interpret it, is if it's above 1, it indicates that the covariate that's positively associated with the event probability and thus negatively associated with the length of survival. So like if the hazard ratio is equal to 1, there's no effect. If it's less than 1, there's a reduction in hazard. If it's greater than 1, then it's an increase in hazard. I'm gonna stop sharing the presentation and we're gonna go to the R demo. And please give me a thumbs up if you all can see the demo right now. Or you can unmute yourself and say that everything looks good. Thank you, Joshua. Okay, so for this demo presentation, or the demo presentation is basically based on the statistical tools for high throughput data analysis. And I'm going to be sharing on my last slide all the references that I'm using for this presentation. But so we're going to be using 2 R packages, the survival one for computing survival analysis, and then the Statbyte package, which is used for summarizing and visualizing the results. So we're going to go ahead and install the packages.
Andrea, we have a question potentially, or like, do we have a question, Armel? You can ask now, I think.
Yeah, yes, you can
As
go
we
ahead and ask
go.
right now.
You can put questions in the chat or ask them as you have them.
Yeah, I have a question. Yeah, my name is Armel, and PH AP Bio. So my question is, how different Cox regression is from multiple or linear regression?
You're taking time into consideration. So it's mainly used for longitudinal studies. So whenever you have a multiple regression, you're just like looking at one population at one point in time. For this one is like you're looking at how that outcome changes over time. That is the difference. One of the main difference, yeah.
I mean, I think I would add to that. You're kind of in linear regression. You're not modeling differences in rates between groups. In Andrea is exactly right. It's longitudinal data that you use this for to get rates, rate differences, the rate of event between groups. So how fast does one group develop an event compared to another? And also one key thing, I guess you could model differences in survival time using linear regression. Maybe that's where it's stemming from, but it doesn't account for censoring. So that's like one of the key features of Cox that makes it a much more robust method because we account for you know, like if somebody doesn't have an event during our observation period, we account for that. Go ahead.
Okay. Okay, so once we install the packages, we can go ahead and load them. So again, the survival package is for computing the survival analysis, and the Statbyte one is for visualizing the results. Tidyverse and dplyr is mainly for data manipulation, data cleaning, creating variables, etc. And then sometimes it's useful to also include your ggplot, just if you want to visualize some of the variables. Oh, Young, is there a specific issue that you're having?
Yeah, and do you have our studio? In order to do this, you have to download our studio.
Our studio.
Or
okay. Where I can download it? Because
I will put that in the link.
Okay, thank you.
Okay. So we go ahead and we're gonna load our libraries. And it's okay if you get this warning errors, it's totally fine. Okay, so we're going to be using the lung cancer data that already comes in the survival R package, this one right here. I know that I was having issues loading the data using this command earlier. So if you're having any issues, yep, it says that it's not found. You can go ahead and use the same link that Dr. Johnson dropped in the chat that leads you to our box folder. It has the data set. So I've already saved it in one of my files. I'm using the command read.csv because it's a CSV file. And I go ahead and load my data. Any questions so far? Okay. So with this function,
Do we have? Oh, yeah. Sorry. My question is: do you take into account the distribution, the type of distributions of variables that are going to be modeled by Cox regression? Like you?
No, and you can correct me on this, Dr. Johnson, but I don't think either the Kaplan-Meier, the log rank test, or the Cox regression take into consideration the distribution. All of them are non-parametric tests.
That's correct. Sorry, it was taking me a while to find the link. You have to download R and R Studio. And I think you can access them both at the link I just posted. I would just, if I were you, I would just follow along if you don't have R Studio already installed, and then you can work on this later. You can run this code if you want to try it for yourself.
Mm-hmm. And then after the specified time for this presentation as well, I have my stat lab hours. So if you want to just like do a walk-in appointment and you want to go over this demo or any other questions that you may have after this, you can just like use the link to my Zoom meeting, and then I can walk you through this. Okay. So we're looking at the first 6 observations that what this function does. We can also open this, our data set, data frame on the environment, and then you can see the type of variables that we have in this data set. And now we're gonna get to the data management part of the presentation. Okay, so as you can see, we have variables inst, time, status. So inst means institution code. Time is the survival time in days. The status means the censoring status. 1 is censored and 2 is dead. Age is in years. The sex here has been coded 1 as males and 2 as females. And we're going to be dealing with that later as well, right here. We're going to be recoding those variables, just because if you don't code as 0s and 1 whenever you're doing, well, not just for sex, but any variable really, your reference category is going to be the first variable that appears in alphabetical order. In this case, it would be female, or you would have to specify which one you want it to be your reference category. But whenever you have something coded as 0, that's going to automatically be your reference category. In this case, it's going to be male. Okay. So sex, PH is COG. That is a performance score. If I'm not mistaken, it stands for Eastern Cooperative Oncology Group. So it describes a patient's level of functioning in terms of their ability to care for themselves. So it goes from 0 to 5, 0 being good and 5 being dead. Later during the data management part, I created another variable for this one, which is ecogcat. I usually do this whenever I'm doing data management, just because I want to see what each number stands for. So as you can see, like 0 is fully active, 1 is restricted, and so on. So PH PH cardinal and PAT cardinal, that's a different score. Basically, it's the Karnofsky performance score. It goes from 0 to 100, 0 being bad and 100 being good. The PH one is the one that's rated by the physician, and the PAT one is the Karnofsky score that each patient gives to themselves. So meal cal is calories consumed. WT loss is weight loss. So we are going to go ahead. Before I start renaming variables, I usually get the column names just to make sure that I'm not making any mistakes whenever I'm typing this and typos. Rename our variables, and we are going to recode our sex category. And again, I usually do this whenever I'm doing data management just because I want to see what each one stands for. But we're not going to be using it for, at least not this variable, for analysis. Okay, so we're gonna, any questions so far? Okay. So we're going to be fitting the Cox regression using the covariates age, sex, ECOG score, and weight loss. We are going to be computing univariate Cox analysis for all of these variables. And then we're going to be computing them all in a multivariate Cox analysis just to see how each one of these variates perform by themselves. And then the multivariate analysis to see how they impact the survival together. Okay, so we're going to run our first one, Uni1H. And then the summary function actually gives you a better report of all the statistics that you're going to be needing for assessing the impact of this variable. Any questions right now? Okay, so you get this report. If you look at your Z value, or the one that's marked. Oh, thank you, Dr. Benson. This is going to be your Wald statistic. In this case, is 0.04, meaning that it is less than 0.05 and it is significant. It's basically saying that H has a statistical significant coefficient, right? And this will be also interpreted as our betas. The regression, so when we look at our regression coefficient, what truly matters is whether it's positive or negative. In this case, it is positive, meaning that age, or in this case being older, increases your chances of death, right? So first, we're going to be looking at our Wald statistic, our coefficient. The next thing that we're going to look at is our hazard ratio, or our exponentiated coefficient. In this case is 1.019, meaning that age increases the hazard by 19%. So being, and finally, we look at our confidence intervals. So technically, because they're not crossing 1, or 1 is not included, so it's 1.001 to 1.037, they are significant. Okay, so we are going to run our univariate analysis with sex this time. Again, we got our summary of the results. We're going to be looking at how significant our coefficients are, in this case, sex. It is less than 0.05. So that means that our coefficient is very significant. Once again, just to remind you all, our reference category in this case is male, that is coded as 0. So this coefficient that we're seeing refers to females. It is negative, and it is also 0.53. So the second, a positive sign means that the hazard of death, the hazard of death is higher, and therefore the prognosis is worse. In this one, since it's negative, is basically saying that being female is associated with having a lower risk of death, lower survival rates compared to males. Let me know if you want me to repeat anything right now, or if you have any questions. Hi, Ramel. Yes, go ahead.
Yeah, I have a question. This question might be basic. We know a hazard ratio is the estimate we get from Cox regression. So my question is, what does it represent? Like, what does it mean, an hazard ratio? Like, what is the definition of an hazard ratio?
Okay. It's basically your probability of having that event in the observed time compared to whatever other category that you're looking at. In this case, we're looking at the difference in sex, females versus males, and our reference is males. So this is basically saying that being a female is associated with a good outcome. Like being a female is gonna, like you're gonna survive longer compared to males. Or as Dr. Johnson is saying, like think of it as an incidence rate ratio, yes. Did that help or no?
Yeah, thank you. Thank you so much.
And just thinking back to epi, and we do like, remember incidence rate is the number of cases over the total time at risk. I like to think of hazard ratios as modeling that incidence rate ratio. You can also do it with Poisson, but Poisson regression is a little bit, it's kind of a different concept because you don't really have time to event in Poisson. It models incidence rate, so I don't want you to get confused, but this really models the rate of an event. We're all gonna die, right? Sorry to be gloomy, but so it models the rate of our, if you want to think of this example, the rate at which we proceed towards death according to our characteristics. So we know that on average, smokers have a higher rate of death than non-smokers. So they die generally early. So this is a way where we can model that kind of phenomenon.
So I don't know if I can ask. So based on what you just said, how different is it from the relative risk?
So relative risk is a very vague phenomenon, which has actually no, you can't tie it directly to a measure of association if you look through the literature, because some people will use a relative risk to mean an odds ratio. And some people will use a relative risk to mean a cumulative incidence ratio. So what I generally tell my students is we need to have, when we report, like in our results section or our method section, we need to report the exact measure that we're modeling, because I would just say relative risk is a generalized name for a measure of association. It's confusing, I know. So we never really model, there's no models for relative risk. It's just an abstract concept that's used to mean, you know, odds ratio, hazard ratio, the incidence rate ratio from Poisson model. People use it very vaguely.
Thank you so much.
And thank you, Junho, and hopefully I'm pronouncing your name correctly, for sharing all those resources in the chat. Okay, perfect. So we were looking at the hazards ratio, and in this case, being female, in this case coded as 1, reduces your hazard, in this case death, by a factor of 0.59 basically, or 41%. We're also going to be looking at our confidence intervals. Again, it doesn't include one, so that means that these are significant. And something that I did not talk about before in the last univariate analysis is the importance of these three tests, which these are basically omnibus tests that talk about for the overall significance of the model. Okay, so we can go ahead and run the following univariate analysis, which is looking at the ECOG score. So again, it is statistically significant because it's less than 0.05. Less than 0.05, meaning that ECOG score has highly statistical significant coefficients or betas. It has a positive coefficient, meaning a high risk of death, and a hazard ratio of 1.61, indicating a strong relationship between an ECOG score and the risk of death or poor survival. Once again, the confidence intervals do not cross 1, which means they are significant, and so are the likelihood ratio test, the wall test, and the score test, which talk about the significance of the model. All of these values are less than 0.05, therefore significant. Any questions so far? Okay. And finally, we're gonna run our last univariate model. Okay, so for weight, our wall statistic is higher than 0.05, which means that the coefficients of everything that we're seeing here is not significant. Our confidence intervals also cross 1. That means that our hazard ratio is not significant. It doesn't contribute to the model. Any questions right now regarding the univariate models? Okay, so up until now, we've been running univariate models for each one of these variables. Now, the whole point of a multivariate analysis is to see how all of these factors are going to interact together, right? So we go ahead and we run the test. And we get a bunch of numbers that are pretty much going to be interpreted the same way that we were doing before. So we want to look at our model and the significance. So the p-value for all of this, the likelihood ratio test, the walled one, and the score of log rank test are significant, indicating that the model is significant. Now we look at each one of our variables. So age, sex, ECOG score, and weight loss. And as you can see, sex and the ECOG score have remained significant, unlike age. If you recall, it was significant whenever we run it by itself. Whenever we include all these other covariates, it is not anymore. So let's look at one by one. So age is much less than 0.05 with a hazard ratio of 0.55, indicating a strong relationship between the patient's sex and a decreased risk of death. And the way that you interpret this is if all of these variables that you're including in your model are constant, being female in this case, because remember that our reference category is being male, being female reduces the hazard, in this case death, by a factor of 0.55, or you can also say by 45%. Once again, we conclude that even in the multivariate analysis, being female is associated with a good outcome. In the same way, if we look at, and right now we're looking at our significant variables. If we look at the ECOG score, again, it's less than 0.05 with a hazard ratio of 1.67, indicating a strong relationship between the ECOG score value and an increased risk of death. Yes or no?
Yeah, I have another question. When doing your Cox regression, do you have to make any prior assumptions as to covariates? Do they have to have a linear, you know, to make an assumption for the linear form or anything? Or do we just choose them and adjust them to our model?
Well, you choose them depending on what your study is. But no, as far as I know, you don't. There are non-parametric tests. So I don't think even if one of the assumptions is violated, like let's say linearity or anything like that, you can still run it. And Dr. Johnson, you can correct me again.
I will say all the right-hand assumptions, well, I guess I won't call them right-hand, but the assumption of linearity has to be met. So age should be linearly related to the hazard of death. And so you should check that assumption, and you can check it the way you would usually check that assumption for logistic or linear. Well, I guess it's assumption for both linear and logistic regression as well. So any linearity assumption applies in all regression model types. So a quick way to check that, I mean, you can do like the Box-Tidwell test to see if it follows a linear pattern, but you can also categorize age into meaningful categories and look to see if it's generally, as you increase in categories, does the hazard ratio increase linearly, or the log hazard linearly, or increase or decrease in a linear fashion.
Thank you, Dr. Johnson. Armel, did that help?
Yeah, thank you. Thank you. It was clear.
No, of course. Okay, where were we at? Okay, so the ECOG score, 1.67. So a higher ECOG score is associated with poor survival. Again, if we look at our confidence intervals, it doesn't cross 1, so it is significant. And then we look at age just because it was significant whenever it was the only variable included in the analysis. But of course, it changed once we included these other variables. Our p-value is now 0.16. Our hazard ratio is 1.01 with a 95% confidence interval that does include 1. This is basically saying that whenever we're holding all of these other covariates constant, every single increase in year, like an additional year of age, induces the daily hazard of death by 1.01 or 1%, which is really not a significant contribution. And finally, the p-value for weight is still not significant. It's 1.17, or for the hazard ratio, we have 0.99 with a 95% confidence interval. Again, that includes 1, meaning that the contribution to the model is also minimal. Any questions so far? Okay, now we're going to go ahead and visualize the models. So for this one, we're only going to be visualizing our reference category. So basically males. Okay. So the horizontal axis represents the time in days, and the vertical axis shows the probability of surviving or the proportion of people surviving. Every single drop that you see on the graph indicates an event, in this case, death. And every single mark on the curves means that a patient was censored at the time. Now, again, this is only looking at our reference category, males. Now, if we want to see how these are different, or our reference category is different, let's say, for example, from our females, if we're trying to like make or see that difference, we're gonna go ahead and create a new data set. In this case, it's gonna be survival sex, including all of our variables of interest. As you can see, sex, male, female. We're basically constructing a new data frame with the rows male and female. The covariates are fixed to their average values if they are continuous variables, for example, age. And to their lowest level if they are categorical variables. We're gonna go ahead and plot both of our survival curves. And we're gonna see the difference in males and females. Again, our x-axis is time and our y-axis is the survival probability. And what this is basically saying is that at our time 0, at the beginning of our study, the survival probability is 1 or 100, right? And as the time goes on, we can see that curve dropping, and it starts pretty early. You can see pretty early the difference between males and females. At time 255, for example, the probability of survival for the males, which for the males is approximately 0.55 or 55%, and 75 for sex 2, in this case females. Any questions so far? Okay. I'm going to stop sharing and then go back to the PowerPoint presentation, unless anybody else has any questions regarding the R Markdown file. Okay. Okay, this basically concludes my presentation. My stat lab hours are on Wednesdays from 1 to 5 and Thursday from 8 to 12. Again, software expertise, primary is SPSS and secondary data management in R, and I'm slowly learning how to run some of these analysis and more complex analysis in R. And these are the references that I used for this presentation. Thank you.
Thank you, Andrea. And this will be available maybe today or tomorrow on the Stat Lab website.
Great. Thank you everyone for being here.